Okay, so let me get my little pointer thing. This is going to be a brief PowerPoint. Basically, just going to talk about a different kind of acid, an acid that gives off more than one proton. Up to this point, we've only been talking about acids that can only give off one proton. Those are called monoprotic. These are called polyprotic. And here's some example. And here's some example of inorganics. Organics will have carbon in them usually. So I know this has carbon in it, but the organics are the ones that we find in life molecules and living systems. These are found in living systems too, but they don't actually interact as part of the process, metabolic process. But anyways, so let's continue talking about, and we're going to look at phosphoric acid. And we can see that phosphoric acid has 3 hydrogens to give off, and so that has 3 different Kas. And we're going to study this guy a little bit more. Next slide. Okay, so here's the first one, H3PO4 gives off the H plus, and this is the Ka. Second one gives off H2PO4, gives off the H, and now makes HPO4 2 minus. Then finally, this guy completely dissociates, and so you have H plus PO4 3 minus. Okay. Now let's take a look at the Kas here, and we notice that they're different. And so let's just take a look in terms of their quantitative, how different they are. So let's just look at the exponents here: 10 to the minus third, 10 to the minus eighth, 10 to the minus 13. Okay, so the Ka basically is an expression that tells me how much product I have per reactant. So this here, 10 to the minus third, basically means 1 out of 1,000. That means you have 1 set of products per 1,000 reactants. Okay. Now if we go down here, this guy here, 10 to the minus eighth is about 1 in a billion. Okay. And so that means one of these guys was 1 out of a billion of these guys was split into this pair. And then finally, this guy here, this number here, 1 over this 10 to the minus 13, which is about 1, which is 1 times 10 to the minus 13th, which is 1 out of 10 trillion. So this expression tells me that only 1 out of 10 trillion of these will split apart. So if we look at the relative acid strength, this guy up here is going to have the highest acid strength. It splits apart easier and more than these guys down here. In fact, this guy splits apart about 1,000,000 times better than this one, and compared to this one, on the order of 10 billion times more. Okay. And so what that's really going to tell us is that the majority of the H plus will come from the first ionization step. And then what we can kind of do is ignore the other ones. So each ionization makes a contribution to the H plus. If we were really do this equation precisely with all the Ks working out, and we could do that these days with computers and things. It actually figure it out, and it's not that hard using calculators. But back in the day when we didn't have this, we learned that there was kind of an easy way to do it, and it still gave a very satisfying answer. Okay, so what we notice is this, and this number here is on the order of 1,000,000 times larger than this number, maybe even 1,000,000,000,000 times more than this number. So why is it? Why is this stronger acid? Why is it release H plus better than this guy down here? Okay, and the reason why it can this guy can release H plus better is because these guys have negative charges on their acids. So this guy has a H2PO4 1 minus on it, and so that proton, it's harder to lose it because it has a negative charge on the acid. And this guy has a 2 minus charge on the acid, so it's really hard to pull off it. So this guy here is the easiest one to lose the DHs. Okay, then here again, usually the second or third step is on the order of 10,000 to 1,000,000 times more difficult than the previous step. So what we just basically have to do is essentially all the H's come off the first step, and then what we can do is ignore second step or third step if needed. So let's take an example of this. Okay, so let's say I have some ascorbic acid. It's a diprotic acid with Ka 6.7 times 10 to the minus 5th. And Ka 2 times 10 to the minus 12th. And what we want to do, just like in previous reactions, figure out the H plus, which pH, the final concentration, the equilibrium concentration of all of this. Okay, and we're going to use the two given Kas and figure this out. So first of all, what we're going to do is we're going to use this guy here, Ka1, to figure out H plus, pH, and amount of acid. Okay, because most of the H plus is going to be coming from the first step. Now we want to know the second step because that's it. So what we are going to do is take the information we get from these guys and use it to figure out this down here, because what we'll have is after this we'll have H plus, we'll have K2, we'll have this value as well, and then we can just plug it in. Okay, so the first step is to figure out the H plus, pH, and find all three of these guys at equilibrium. So we start at 0.075 molar, and the reaction moves to the right. Minus x, plus x, and plus x. The x here, as we've been talking before, it's hardly significant, so you can leave it off. And then we take that and we plug that into the equation, those numbers. So we have H plus over the conjugate base, times the conjugate base over the acid equals the Ka1. And so we substitute in the numbers and we get the amount of H plus and the amount of conjugate base are equal both to 2.2 times 10 to the minus 3rd molar. Okay, so the pH is going to be log of 2.2 times 10 to the minus 3rd. Okay, now what we're going to do is we're going to take this value here, the conjugate base, to figure out our amount of the conjugate base of the second acid. All right, so here's our conjugate base from the first part. Here's our H plus, and here's our conjugate base that we want to find. And here's our equation. So we're saying that H plus doesn't change, and we're saying that this amount, this conjugate base, doesn't change as well. All right, so you start off 2.2 times the minus 3rd. This is also 2.2 to the minus 3rd. That's where our starting is, and this hasn't changed. So the reaction is moved to right to make some product. Minus x, plus x, and plus x. Okay. So this is going to have hardly an effect on this number because this number is really low, 10 to the minus 12. And it's not going to have hardly effect on this number too, because minus 12 is way smaller than minus 3rd. Okay, so we can neglect both those. All right, and then what we have is 2.2 times 10 to the minus third times this quantity, which we call y, all over our conjugate base from the first. Plug them in, and you get this. And then you get the concentration of C6H12, the second conjugate base, says 2.2 times 10 to the minus 12 molar, which is really tiny, and you really won't even hardly notice it, at least most experiments. Okay, so that's that, and I think I got one or maybe two more slides finally to get you, and we're almost there. Okay.